says that substituting in the equation here, he obtains that equation. But you know, I know that in printed form you can always there can be always missprints because I did not believe I did it myself and I did not come to that equation. So something was wrong. Therefore, I started calculating the symmetries and found this operator. And then invariant solution, this is correct form, and came here. And then initial conditions become like this, and so on and so on. But I found that it has also some certain first integral conservation law, which can be interesting physically. I did not investigate that. But also found some other case of constant m, which is there. Constant m. You see? In this operator. And also this m comes from here, this m. So for several m, there can be different symmetries and different invariant solutions. So just it's again, I did not do it up to industrial application, but equations coming from industry. Okay? For example, it was one of them was found by Moffat himself, and I found another one. You see, this was, I think, found by Moffat from physical point of view, and I found from mathematical point of view. That's another special case of with singularities. And this was, I think I still have 5 minutes. Just I thought that not that many papers on investigating by means of group theory models from medical sciences. So just I became interested in that and found a serious paper of several people for tumor growth, which is today a very important problem in the world because so many people have oncology problems. And this is one of the models which are quite serious. So 2 equations. Of course, in the beginning there are 3 equations, but one of them can be eliminated in certain approximation and so on. In mathematical modeling, what is important? You have much more freedom. Because when the equation is just given and you come mathematicians start investigating, you can stuck there because of this equation does not have symmetries and so on. But when you take practical problem, there is so much freedom. You can choose that, or you can change yourself, because if you come deeper in how you make the model, you can make another equation, not exactly that one. So here also it was 3 equations. It's difficult to investigate, too much calculations. Then we eliminated one of these functions and came to 2 equations. And for them we calculated symmetries with my student in Sweden. And for that situation, we found one symmetry and invariant solution. So it was Sevström from Sweden, 2004. And here is the solution. And there are some conditions for the functions, so that these conditions satisfy the solution. Conditions are given here. It should be these conditions. There are functions f and g, unknown functions. You can make group classification, for example, but these conditions are important. And using them, we obtain the solution, particularly having, this is the solution. But again, I did not have time, of course, I did even visit the oncology central institute, Karolinska Institute in Stockholm, to discuss with the head of the Department of Oncology. And what was interesting, he told that it was a very interesting person, and he told that when they treat tumor, they are using some medicine, and they had some problems. And the problem is how much medicine to give and how often, and so on and so on, depending on many situations. And of course, they could use the models in order to, for each person, for each case, it would be different, for each type of level of the disease. But he thought that our director told no differential equations, because forbidden even to pronounce the word differential equations. Instead, they used just a word. I told you in first lecture in modeling with functions. So that was, he said, that's enough for us. And of course, he says that we make a lot of mistakes, but we will try to improve each time we draw another one just by chance. Of course, a lot of problems, yes. I think when you go to pollution problems, there could be so many models, interesting models for mathematicians. And they, for example, in Brazil, there are so many work for mathematicians because they have a lot of insects, dangerous insects, and diseases and so on. And then mathematical biology becomes very attractive science there. So what else we have here? Yes, now I will just a few words about that, then we'll make a, because I think we have another 10 minutes, yes? No? 4 minutes? Oh, I think it's enough. It's just from my student thesis. When I finished university, Arsen was my supervisor. He calculated symmetries, found new symmetries for gas dynamic equations, and one of them is for gas dynamics with two-dimensional gas dynamics with special polytropic gas, with special value of the polytropic constant, gamma equals 2. Then it has special symmetry, and it describes shallow water. A very well-known shallow water model. And my problem was to investigate this model from point of view of groups and make also classify, find optimal systems of all 1, 2 parameter groups. So I found them, and for some of them, of course, I investigated invariant solutions, but calculated. But one of my interpreted physically. This is my So here we have the system. U, and U is the velocity, of course, H the height of the water it's on the flat bottom, shallow water flowing. And G is, of course, usual gravitation constant, and two-dimensional case X and Y on the plane. And these are operators which I use. There are many of them, but I use 2. So X1 is the rotation in XY plane, and in also U and V components of the velocity. And this is special symmetry which does not exist for usual gas dynamics, but it's only for the special gamma. And in the case of gamma equals 2, exactly this one. So I have to calculate invariance for 2 operators, not for 1, but 2 operators. And the equation you see has 3 variables, t, and t, x, and y. 3 variables. In order to obtain the invariant solution in terms of ordinary differential equations, we should reduce the number of dependent and independent variables by 2. 3 minus 2, then 1 variable remains. And for that we need, of course, the group with a rank of coefficients equals to 2, and this is exactly this one. In this case, the rank coincides with the number of operators, x1, x2. So we have to find the invariants. Finding those invariants, we substitute invariant solution form to the equation and obtain a complicated system of differential equations. And solving them, so this is, by the way, one of invariants here. So solving them, I obtain the solution given here. It was long calculation, but the first time I was working with invariant solutions with group analysis as a theoretical mathematical tool. So it was very interesting. And later on, I made a picture of that using, I think it was done using mathematical. And here is the solution. Even though we made, but she's not here, one of my members of my laboratory in Lecture4, I asked her to make a small movie, how this work is moving. Of course, it's clear that since of the gravity, it was flow and go down, becomes steeper and steeper, or not steep, but shallower. And you can see, just this is the difference. If you have just that picture or formula, it's one impression. When you see how it really flows, you can compare with the real fluid dynamics. It's more attractive for students. That's why I think that we should make that kind of pictures. People do it, of course. So that's it. And then we will stop here and talk a little bit about also higher dimension.